Hey guys, thanks for staying late. I know I'm the last one. My name is Sam Friedman. I'm from Chainlink Labs. I'm a solutions architect. I work on a couple different projects at Chainlink Labs. One is we have an incubator with 77 projects. I'm the technical lead on the incubator. If you want to learn more about that, just contact me afterwards. And my second role is as principal solution architect for CCIP, cross-chain interoperability protocol. It's a product we've been working on for several years and launched on testnet at ETHCC in July in Paris, and launched on mainnet in July in Paris. I was on testnet long before that, in January of this year. And I'd like to share more information about that. So one is, I'll start off with, why is interoperability important, or why do we need a standard for interoperability? So in this, I worked hard on my slides, but I probably could have kept it a lot shorter if I just scrolled through crypto Twitter. But right here, if you read closely, you'll see that Curve Finance is explaining how to participate in 3 of their pools. Either you want to trade in their pool or you want to provide liquidity. And to do so, you have to use 2 different bridges. And one of the bridges you have to use 2 different ways, one through the UI, one directly through the Explorer or something else. Also, there's a good admission that even with explanation, it's really difficult to use. It's not obvious, really impedes adoption. And lastly, just another admission by Brian Armstrong that it's really confusing for the users, and I'll show you some evidence of this right now. More complaints on crypto Twitter. By the way, there's a lot of consensus on crypto Twitter about this, and I think everyone in this room probably agrees. This is not a contentious point at all. Liquidity fragmentation is a problem. It makes things confusing. It makes composability very difficult. It makes liquidity management very difficult. But more evidence. So lending protocol on Avalanche has USDC and Tether, but there are 2 different markets for each of those assets. Liquidity spread out almost evenly. One of my favorite decks is also on Avalanche. USDC, so a couple stable coins or pegged coins. USDC, USDC, BTC, BTC, Tether, Tether. So the problem is everywhere. DEXs, lending protocols. So why does this happen? There isn't a standard for interoperability. There are multiple bridges out there. Different assets support different bridges. Different protocols support different bridges. This is very painful for developers. They have to maintain separate code sets depending on which bridge they're using. And leads to a lot of complexity, which leads to lots of costs, liquidity fragmentation, excessive trust assumptions if you're using multiple systems to do the same thing, impedes adoption because it makes things difficult, and overall inhibits growth, which is why we're here to solve that problem. So it's not just enough to solve the interoperability standard problem. We have to do it in a secure and reliable way. And there's plenty of evidence. I think both of the presentations prior to mine hit on this point as well. These are not all of the big bridge hacks from the last year or so. It's not even the most recent ones. Unfortunately, I prepared my slides too early, and I'm missing a couple of big ones. But these are pretty big numbers for our industry. Right. And then when we design an interoperability standard or an interoperability protocol, there are lots of things to consider. So there are interfaces that users interact with. Are these contracts immutable? Can they be changed? Who owns them? They're supporting contracts. Are they upgradable? Who can make changes? What's the process? There are off-chain components like relayers or oracles. And is there any kind of verification or transparency or understanding of how these systems are composed? Who owns and operates them? Are they secure? Are they reliable? So I work for Chainlink Labs. We're in the cross-chain interoperability protocol space. Why would we do that? People say, hey, you're an Oracle shop. Why cross-chain? Well, Oracle solve a basic problem, which is they make off-chain resources available on-chain. And a lot of us know, most of us know Chainlink for data feeds or market data. That's an oracle that provides data, off-chain data on-chain. But data is just one type of off-chain resource we might want to make available. So our price feeds provide price data or index data, commodity data for crypto products, equities, et cetera. But we also provide computation as an off-chain resource and make that available on-chain. We have an automation oracle. We have a functions oracle that connects smart contracts to JavaScript and the internet. So off-chain computation is just another type of oracle. And then when it comes to cross-chain, that off-chain resource just happens to be another blockchain. So all of these products fit very well within our product set or portfolio of products, solving the same type of problem. We make off-chain resources available on-chain. Now, there are a number of ways you could design an oracle system, and we've seen lots of different examples of this. We've seen single entities with a single server. We've seen these fail catastrophically just in the last few months. We've seen systems set up multiple servers but owned and operated by the same system. We've seen organizations set up a network to run processes, but a single network, and it's the nodes or components on this network are often owned and operated by the same entity. And then we've seen organizations use multiple networks to secure different components of a system or different feeds. And at this fourth level with multiple networks very accurately describes Chainlink oracles that provide price data on-chain. So each price is supported by a different oracle network. Each node in that network is owned and operated by an independent node operator. With cross-chain interoperability, we took it one step further, and we used these existing decentralized oracle networks plus a second type of network called a risk management network. And I'll describe the function of that risk management network in a moment, but the key point right now is the risk management network was designed by Chainlink Labs, but by a separate team using different application architecture, different software libraries and programming languages, and a different consensus mechanism. So Chainlink has been developing decentralized oracle networks, using them for the last 4 years to secure trillions in transaction value. And that decentralized oracle network architecture uses something we called OCR, or off-chain reporting. This is a Byzantine fault-tolerant off-chain consensus mechanism. So all the nodes in this network, again, each node is independently owned and operated, not by Chainlink Labs, but by node operators that are KYC'd, have gone through a vetting process, et cetera. Those nodes communicate with each other and come to consensus off-chain on an answer. One of the nodes creates a report with all the signed answers from each of the nodes in that network, and then one node publishes that report on-chain. CCIP is a plugin on top of that network, just like price feeds, just like automation, just like functions, just like proof of reserve. There's all the same architectures as existing products, so there are no new trust assumptions. And then while you can build things like token bridges with CCIP, it would really be a disservice to call CCIP a token bridge. That's just one of many different use cases that it can satisfy with this architecture. So we've seen our users build token bridges, satisfy cross-chain governance requirements, embed CCIP in wallets or other protocols to support all kinds of cross-chain use cases that we never thought of. Now, the last component you see here on the right is the risk management network, which I explained is a completely different architecture, and I'll explain its role in a moment. At a very high level, CCIP enables an account on a source chain to send a message to an account on a destination chain. And those accounts can be externally owned accounts or smart contracts. And those chains can be public chains or bank chains or private chains. And those messages can include data or tokens or both data and tokens. Now, sending data only, that would describe a couple different use cases by one of our launch partners, Aave. Aave has two different governance use cases that use the data handling mechanism of CCIP. One is They enable Aave token holders on remote chains like Avalanche and Polygon to vote on mainnet proposals without having to bridge their tokens. So votes can be cast from remote chains, and CCIP delivers that vote count or accounting back to the mainnet. The second use case that Aave has is also governance and uses the data handling capability, and that is also related to governance. And when mainnet proposals pass, the payload is sent to the remote instances of Aave and other chains as data in a CCIP message. For token handling, I can point to another launch partner, Synthetics, that built their own token bridge called Synth Teleporter. The Synth Teleporter enables Synthetics or SNX USD holders to send SNX USD between Ethereum and Optimism, where SNX USD is burned on the source chain and minted on the destination chain. That can go bidirectionally. Synthetics built the UI and some supporting contracts to embed the application or the token bridge in their decentralized application, but they use CCIP to burn and mint the token and send messages between those chains. And then a use case for including both data and tokens might be exemplified by work we did with ANZ, the bank in Australia, that sends stable coins between an Avalanche subnet and a public chain to settle, handle DVP or delivery versus payment use cases. So you can send stable coins with instructions to swap those stable coins for security. Just a few examples. All right, and let me talk a little bit about our architecture and our defense in-depth approach to security. So I've already explained that CCIP enables an account on a source chain to send a message to an account on a destination chain. That message goes to a router contract. This is an immutable contract on every chain that CCIP supports. The router contract will send that message to an on-ramp. There is a separate on-ramp contract for every supported destination chain. The on-ramp contract checks that the message is compatible with the destination chain. So the message might have destination chain specific parameters. On EVM chains, for example, that might be a gas limit. If the on-ramp contract validates the message and that message has tokens, then the message is checked against a token pool contract. Every token that CCIP supports will have a token pool contract. And the token pool contract primarily does two things. One is it checks a rate limit. So every token issuer can define their risk exposure in terms of a rate of tokens that they will allow to pass between any source and destination chain. As an example, Synthetics set a rate limit of 100,000 SNX USD per 10 minutes. So if any message surpasses that threshold, it will revert. The second thing the token pool handles is the token handling mechanism. So are we burning tokens on the source or are we locking tokens on the source? And then on the destination chain, the token pool contract would handle either unlocking tokens or minting synthetic versions or native versions of that token. After everything on the source chain passes, an event is emitted, and then nothing else happens until source chain finality. Most of the chains we've integrated with today have a finality flag, and CCIP waits for the finality flag to protect against reorgs. In cases like Polygon, then we wait a safe number of blocks. So the first off-chain action is handled by the committing decentralized Oracle network. The committing decentralized Oracle network is the same application architecture as the decentralized Oracle networks that secure price feeds, so no new trust assumptions. The committing decentralized Oracle network, or DON, creates a Merkle tree of all the transactions between a particular source and destination chain, and publishes the Merkle tree root in a commit store contract on the destination chain. And if you don't know what a Merkle tree is, it's a data structure that's used to support a cryptographic proof or cryptographic process. So after the committing DON creates the Merkle tree and publishes the Merkle tree root in the commit store contract on the destination chain, then the risk management network snaps into action and performs the exact same task. So secondary validation, except done from a separate network with different application architecture and network architecture, different software libraries, different programming languages. Creates the Merkle tree, or each node in that network individually creates the Merkle tree and then checks the Merkle tree root against what's already on the commit store. And if they match, then those nodes cast blessings on the commit store, and if they don't match, they cast curses on the commit store. Once that Merkle tree root on the commit store has received a threshold of blessings, then the third Oracle network or decentralized Oracle network comes into action, and that's the executing dawn, which can submit transactions from the source to the destination chain along with a Merkle proof, which has been validated by two separate decentralized Oracle networks. It's a lot. All right, so a couple points. I mentioned that the router contracts are immutable. They'll never change, but there are some supporting contracts like the on-ramps and the token pools. Those are upgradable, but they are time-locked. Chainlink Labs does not own those contracts. At best, Chainlink Labs can submit proposals to upgrade those contracts, and the owner can veto or has 24 hours to veto those proposals. One, there are no new trust assumptions with the committing dawn and the executing dawn. Those are the same Oracle networks we've had in place for 4 years, securing trillions in transaction value. And then the second type of Oracle network we use is a completely different architecture. The node operators in all these networks are not Chainlink Labs, they're independent, and the operators in the risk management network do not overlap the operators in the other networks. Token issuers can set their own rate limits. And the risk management network has one more role. So in addition to creating those Merkle trees and blessing the Merkle tree roots, it also constantly monitors the on-ramps and the off-ramps on the source and destination chains for anomalies or abnormal transactions. When it detects something abnormal, it'll cast a curse on that network and pause CCIP operations on that network. So the system is designed to favor safety over liveness. Right. So very high-level architecture and flow for CCIP. This is a standard we think we're well positioned to set. What we did for security, we'd like to do for interoperability and bring composability to the space. But we can't do it alone. We have to work with partners. So I've already mentioned a couple. Aave adopted us for governance. Synthetics adopted us for token transfers between Ethereum and Optimism. Some of you may have seen the news. This summer, we completed our second proof of concept with Swift, where we connected banks to bank accounts or banks' blockchain accounts on private and public networks and enabled banks to send messages, tokenized assets like bonds between private and public networks. We've also been working with the member banks of Swift, like ANZ also published their report, and DTCC also published their report, where we're connecting private networks and public networks and sending tokenized assets. And then lastly, we have a network of partners that we work with. So I mentioned earlier my role in Build, our incubator. So several of our Build partners, being part of Build, have been involved in our beta testing of CCIP, but have also started adopting it on test nets and mainnets, preparing to go live. Folks Finance, they're here today. I don't think they're in the room, but they're at the conference. They are using CCIP to build a cross-chain lending protocol where users can lock collateral on one chain and then borrow against that collateral on a different chain. So that's most of CCIP. I think everyone understands or expects that there will not be one network to rule them all. There'll be lots of heterogeneous networks. We want to be the standard. We want to bring security, or what we did for security on data feeds and computation, we want to do for cross-chain interoperability and bring about ultra composability, have the banks use the same technology that we use, and grow, solve real-world problems. That's it for me. Thank you.